Really, what I'm going to do today is in the video is talk kind of about what we talked about today in class and kind of link it a little bit to what we'll be doing in the next couple of sections. And so we'll be looking at a lot of pictures and looking at a lot of attributes, characteristics of those pictures, and then comparing them to the equations that they go with. All right, so I'm going to be using this pretty cool graphing calculator that you can use online, or that you can find online. Okay. If you just search for, here's the URL, the address, the web address. If you search for Desmos graphing calculator, or I think if you just go online graphing calculator or something, you can get to it. Anyway, so if you notice, here it is. There's nothing graphed yet. I'm going to pick this one to look at first. And actually, let me put it to projector mode so it looks a little darker. Okay, so this is x squared minus 1. All right, so it's a parabola, is a quadratic equation. Okay, I've got a half a dozen here that I'm going to graph, but really this is the first one here. If you notice, it has one vertex and two intercepts. Okay, two x-intercepts, and we talked about that a little bit today in class, how it's a second-degree polynomial. Okay, so it's going to have at most two intercepts, and here they are, and at most one direction change. All right. So it's going to change directions, going down, 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 and then up. And where it changes directions is the vertex. This is the first example of what is called a relative max or minimum, in this case a minimum. Okay? It's kind of the bottom point. Okay? It looks kind of like the bottom point overall. So I'm going to pause and copy and paste for the first example of a minimum. So here we go. Second degree polynomial, degree 2. One relative minimum, and then two x-intercepts. Well, we'll talk about that later. Okay? Now, it's actually generally pretty hard to find them, but not necessarily for parabolas, and not necessarily for the Desmos graphing calculator, because boom, right there it is right there. Okay? Notice the end behavior from class today. It is up. Well, let me go back to what I can draw on here. It's going up. That's horrible. That's not helpful, is it? Going up as you go to the, as x goes to the left, y goes up. As x goes to the right, y goes up. Okay, let me erase this because that's looked dumb. Okay, so it still has the same end behavior like we talked about and all that jazz. All right, so going back to this guy. Now notice what happens if I say, do that. Changes the end behavior. The leading term is negative now. So let's say negative 2. And it's an even degree polynomial, so it changes the end behavior. The leading term is negative 2x squared, and the leading coefficient is negative 2, and there you go. Now it's a parabola opening down, and the end behavior is different. The arrows are both pointing down. Notice, by the way, and we'll talk about this in a second, this is a second degree polynomial, so we have at most two x-intercepts, two real zeros, two real roots, whatever term you want to use. All right, but it's at most. So if it's a second degree polynomial, sometimes you can have fewer x-intercepts, and this is a good example. There are none. Okay? So going back to the original thing, here's the two x-intercepts, negative 1 and 1. Okay, we'll talk more about those in a bit. All right, so let's look at a different guy. Go away. All right, there you go. 3x plus 6. Notice no local maximums and minimums, so not very important to discuss this. Relative maximums and minimums. It's called local maximums and minimums sometimes too. Mean the same thing. So there's nothing that looks like the vertex of a parabola. And we talked about that today in class. The degree, if you subtract 1 from the degree, that tells you how many times it's going to change directions or how many times it's going to have any maximums and minimums. Here the degree is 2. You're going to have one direction change. One, in this case, local minimum. For our friend, the linear equation, the degree is 1. That's 3x to the 1. So the degree is 1. There are no direction changes. So it's not very interesting with regard to that, but we'll talk about it here in a second when we talk about some other stuff. So boom. That's, ooh, it kept everything up there. So there we go. It has 3 intercepts, which I didn't intend to talk about quite yet, and 2 local maximum, local minimum, or relative max and min. So relative max and min or local max and min, same thing. There we go. Now look at the numbers. Numbers are very weird. It is in general not that easy to find exactly what the relative maximums or minimums are, but that's all right. All right, you just got to know. I just want you to know what they are. All right, and that for degree 3, the most you possibly can ever have would be 2 of them. All right, so let me copy and paste the next example. Okay, and then zooming out a little bit so they can actually see it. There we go. Degree 3, it's the biggest exponent, has 1, 2, 1 relative maximum, 1 relative minimum. And so notice what I meant when I said it looks like a parabola, or it looks like the vertex of parabola, it looks like a bottom point or a top point, but just the bottom or top nearby. So if we zoomed in and only looked at this guy, this part here, yeah, it'd look like the vertex of parabola open and down. It's not what it is. All right, it's got other. It's not the name of it, but it kind of looks like one. If you only zoom in and look at a little bit. Actually, let me use the magic pen. Oops, magic pen. So if you zoom in and only look at a little bit of it, so you can zoom in. Maybe magic pen. Magic pen, yeah, zoom in. Not let me zoom in, that's a heck of a thing. Boom, 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 boom. I guess it's not, there we go. It looks kind of like a vertex if you zoom in. It's not really truly the top or bottom point overall, but if you only zoom in and look at a little bit, it looks like it. Zoom in, you can zoom in close enough and see, oh yeah, it looks like the biggest point. Not really, because if you look, there's stuff over here that's larger. I'm talking about the y values here. Okay, you go over here, it's bigger. Anyway, seems like it's called a local max or min sometimes. So this is a relative max here. Boop. This is a relative min here. Boop. All right. Scroll down a little bit more and talk about some other ones. All right. This guy. Oh yeah. What do I want to talk about now? That's right. All right. So that's it. That's all I wanted to talk about with the local maximums and minimums, I guess. So quadratic. See how you get 1 again, and it happens to be right there. Happens to also be the x-intercept. Okay. Here, same deal. You get 1, 2 local maximums and minimum. Oh, I did want to talk about this with the local maximums or relative maxes and mins. The degree, if you subtract 1 from the degree, that tells you the maximum number of local maximums and minimums. So you can have fewer, and this is a pretty good example because the degree here is 6, but there are actually only the 2 maximums and there are the 3 total relative max or min. So we have 1 at the origin here and then 2 more down here. So this is another good example. So I'm going to take it, put it over here. But yeah, so you might be thinking, wait a second, it's supposed to be the 6th degree polynomial. The degree is 6, the biggest exponent is 6. Why does it only have 1, 2, 3 relative maxes and mins? 1 relative max, 2 relative mins on the bottom. Well, that just tells you the most you can possibly have. So degree 6, meaning if you just arbitrary degree 6, you could potentially have 5 direction changes, 5 relative maximums and mins, but you can always have fewer. And here we go, 1, 2, 3, only 3 of them, and that happens sometimes. All right. Quadratics are fixed. They always have to have a one vertex exactly. 2 minus 1 gives you the 1. But really, once you get beyond degree 2, all bets are off. It can have fewer than the what we've been talking about, fewer than 1 less than the degree. All right, so degree 3 could potentially only have, no relative maxes and mins, no direction changes. Alright, but there we go. Let's talk about real zeros, real roots, or x-intercepts. So here we go. Degree 1 has one real root, one x-intercept. Alright? So let me copy and paste it. Okay, and actually I'll do this with the next couple on here. Okay. And then we'll talk about them. So let me pause it and do that. Okay, so here's all 6 that I had over there. And here's the first 3, and I'll show you the second set of 3 in a second. Degree 1 has one x-intercept. Okay, look at the y-intercept up here at 6 if you want to remind yourselves of that stuff. Alright. 1 x-intercept for a first degree polynomial, 2 x-intercepts for a second degree polynomial, 3 x-intercepts for a third degree polynomial. That is the maximum number of intercepts they can have. Okay, sometimes we call them real roots, real zeros, x-intercepts. Alright, they can have fewer, so here's 3 examples where they actually have fewer than the degree. Alright, second degree polynomial only has the 1. Okay, third degree polynomial only has 2. 6th degree polynomial only has 3. So the degree tells you the maximum number of x-intercepts it can possibly have, and it's possible to have fewer. Okay? So what I wanted to talk about to segue into what we're going to do next is how do we find these real zeros? How do we find these x-intercepts or real roots? Now what's up, if you notice for all these examples, all these things, what's true for all of these x-intercepts, all these real zeros? The y value is 0, negative 0, that's a heck of a thing. Y value is 0 for all of them. Okay, that's a little calculator error. Alright, 0 for the y, 0 for the y, 0 for the y, 0 all for all these y's. So what you do to figure out the x-intercepts is you make an equation. The technique for finding the x-intercept is you make an equation. What do? You say, let's say y is 0. Okay, and that's a horrible 0. Let's say y is 0. And you solve for x. We've been doing that since Algebra 1. For linear equations especially. Subtract 6 from both sides, divide both sides by 3, and you get x equals negative 2. And then, wait a second, that's exactly what it says here. There's your negative 2. Okay? Okay, so if it's a linear equation, it's not even an Algebra 2 problem, it's an Algebra 1 problem. Alright, so that's why we're not really going to do much with it. Okay? Same thing here. Lost it. Where'd it go? There we go. X squared minus 1 equals 0. So that's what all chapter 5 was about. You could do square root method is what I'd do. It's easiest. X equals plus or minus the square root of 1, which is, well, square root of 1 is 1, and there you go. 1 and 1. Or negative 1. Alright? Here, what's going on here? Well, this is what we're going to really learn. We're going to do for the rest of the week probably. Solving equations that are of a degree bigger than 2. Alright, sometimes second degree polynomials, but sometimes ones like this guy. And really, most of the work that goes into solving ones like this involve factoring. So I'm just going to do this one. If you want to solve, we want to know when x equals 0, when y equals 0. Y, 0. Alright, and what do? Well, we solve by factoring. X squared minus x minus 6. Excuse me, x. We factor out the GCF of x. And then we can factor this guy. This is x minus 3, x plus 2. Alright, pause it and try to remind yourself of what I am doing here. Alright, and then lo and behold, x goes with this one, x minus 3 goes with this one, and x plus 2 goes with this one. It gives you the 3 x-intercepts. Alright, and there you go. And that's what we'll be working on for the next couple days.